most of it.
Okay.
Just it's just that I will not be able to be interactive.
Oh, okay.
Yeah. Cool. Okay, so you should be going.
Okay.
Awesome.
So let's restart. My name is Robin, and right now let me introduce some information about our machine learning segmentation project. So our project concentrates on 3D MRI image segmentation, which could hopefully help patients with Alzheimer's disease. And could you move to next slide, please? As a very common disease happen in senior groups, the scientists found, can you guys hear me?
Yes.
Okay, Rohit, could you move to next slide? Yeah. So, like I said before, as a very common disease happen in senior groups, the scientists found the brain of the patients are facing the difficulties of proliferating new brain cells. And here is a picture of the brain slice. And in the center of it, you guys could see there is a hollow cavity part, which has a light blue color that is different from the other part of the brain. This part is called ventricle, and it is a key part in the brain that could generate stem cell for cell proliferation. So like one of the treatment recently for Alzheimer's disease is called deep brain stimulation, that the surgeons could implant the electrodes inside the ventricles, use this long needle to help the ventricles restart. So the stem cell zone could kind of work. But however, since ventricles is in the center of the brain and as a very complicated organ, we have to know the accurate position for the ventricles. And because 3D MRI image could only give us the whole brain image, it is really difficult to know like the precise position for the ventricles. So a traditional solution for this problem is to use physicians to manually separate out the ventricles part from the whole brain image. But it really depends on how does the physician take care of the image data. It requires to be really precise and accurate. So we are seeking for a 3D image segmentation model that could let the computer itself to separate out the ventricles for us. And hopefully it could save time and labors and could help for the further surgery planning. So next I'll let my group member Wan Chen to talk more about the applications.
Hi everyone, next I will talk about the application and data collection. First, I will talk about the application. As Robin mentioned, the main purpose of this project is to build an automatic MRI segmenter. And by using this, the plans for EVD can be made more efficiently. So let me introduce EVD. EVD, also called external ventricular drain. As you can see in the picture here, it is a neurosurgery that's placing the flexible plastic catheter, which reduces the intracranial pressure by distracting the fluid from the ventricles. When the normal flow of fluid inside the brain is obstructed. By making an automatic MRI segmenter, this project is beneficial for enhancing the operability and accuracy of EVD. Next, I will talk about data collection. Next slide, please. So the project is using a set of brain imaging data, which consists of a collection of brain images from adults between 18 to 96 years old, with both genders from OASIS database. The project expects to have 3D whole MRI brain images as input values and 3D ventricle images as output values. So for this purpose, we segmented out the 3D images of ventricles from the images of the whole brains by using a software called 3D Slicer. As you can see in the picture here, it shows the image of ventricle that we segmented out from the whole brain in 3D Slicer. Next, also in 3D Slicer, we transformed the diagonals of the segmented data to -1, -1, -1, 1, and converted them to a Python-ready format. Since the dataset is not large enough, data augmentation for both inputs and outputs are needed to prevent overfitting. So next, Yakun will talk about data process.
Hi everyone, I will talk about the data carting part. After we load MPZ files into Python as NumPy errors, we found that the output errors are so sparse, which means most of entries are zeros. The reason is that the ventricles are small parts in the brain, so we need to find the ventricles boundary in XYZ axis separately using if statement and for loop in Python. Using this statement, then we got the 87 different boundaries for every brain in order to retain all segmentation information. So we find the largest range of array ventricles in every axis. After cutting, in the slice, you can see the dimension of each image changed from the 176 to 108, 176 to 80, 128, 128. And Raven will introduce the next part, data augmentation. Next slide, please.
Hi, everyone. Since our group only cut 87 brands, we think that the sample size is not enough. Therefore, we need to enlarge the datasets in case of overfitting. Flipping is a good choice. We use NumPy, which has a function NumPy flip to flip the sample horizontally or vertically. Here can see some sections to observe how the brand flips. Then we could get another 87 samples and add them to our original datasets. For the rotation, Yakun and I tried to rotate one sample for 90 degrees, but we found that the dimension of one's array was changing. However, for training the network, we must keep the input arrays aligned. So we decided not to choose this way. We also considered using a package in Python to enlarge slightly the images, but the computing resource kept crashing when we ran the codes. We guess that the spicy zoom is focused on 2D images, so the 3D images made the time complexity much higher. So we still had trouble applying it. Therefore, we only kept the flipping method. Next part is the model architecture talked by Jimmy. Thanks.
So now that all the data are, we have the augmented data, it's time to actually build the model for it to start training. So with Professor's guidance, we found that the UNet architecture for CNN to be the most appropriate method to implement here. This is a structure developed by Olaf Frauenberger and his team for biomedical image segmentation and research paper back in 2015. So we utilize this structure and we slightly just modify according to our needs. And here are some of the changes that we made. One is that we made the padding to be consistent to the basically the dimension needs to be consistent even after processing through the convolution layer. And we also lowered the number of channels for each convolution layer to reduce the excessive parameters, so that our computer can process through the models within a reasonable amount of time. So this architecture has two paths. One's contracting path, and then there's expansive path. And then in the next slide, you will see the visualization of this structure. So as you can see from this slide, the structure itself looks like a U, hence its name. So I'll begin talking about the first part, which is the contracting path. The contracting path follows normal CNN process. So within each convolution layer, the three-dimensional filter applies the padded convolutions and outputs value for each voxel. After two convolution layers, 3D max pooling will apply and take the largest element from the rectified feature map within the cube size of 2. And this then cuts the dimension by 1/8 after the operation. And this downsampling step repeat 4 times. At the bottom, the U, the reduced input dimension will go down to 5 by 8 by 8 with 128 channels. And then we go on to the expansive path where we bring the image dimension back up to the original input size through upsampling output and from the previous layer. So we upsample by basically just double each voxels and then doubling up the size of each dimension. And after upsampling the 3D image is then concatenated with the corresponding 3D image from the contracting path to combine the information from the previous layers to get more precise predictions. And then again, they're followed by two more convolution layers with half of what was the previous convolution, followed by two convolution layer with half of the channel of previous convolution layer has. And in the end, we repeat it 4 times again. It will come back to the original dimension with the final segment output segmentation map. So now Rohit will talk about the steps that we've encountered during this training process.
Thank you, Jimmy. So before reaching to our final model, we had multiple trials, some of which are stated here. So first we trained our original unit architecture with around 300,000 of parameters and on original sample size of 87 images. Here we split the data for 80% for training and 20% for testing. And also to reduce training size, we downsampled each image axis by half so as to we just extracted middle 50% voxels. So we kept learning rate as shown by here, and overall accuracy was 98%, but as the base accuracy is 97%, that is 97% of the pixels do not contain any ventricles in it. So that's why performance of this model was not that satisfactory. Also, another problem was we might have lost some information due to downsampling what we did over here. So in our next trial, we adapted a kind of better strategy for train split, that is k-fold cross validation. So here we implemented 5-fold cross validation, and with the augmented data, that is the original data flipped vertically and horizontally. So basically this is the 3 times the original data size, and we kept the kernel size and learning rate same as above. But still here our overall accuracy was 97.34, which was basically our model was trying to predict the zeros in it and was not satisfactory. So we went ahead for this time for faster run approach, because one of our main issues with trials was training time. So to get the minimum loss in less amount of time, we started with a higher learning rate, that is 10 times the original learning rate we had over here, and then run some epoch and save the model at the lowest loss, and then reduce the learning rate and then trained model again on the same sample sizes we had before. So here we increase the kernel size to 7 by 7 by 7, because so as to reduce the number of parameters. So originally we had kind of 341,000 something parameters, and then here we kind of reduce the parameters by 10-15,000. So which helped us in reducing training time, but the accuracy was not yet satisfactory. So moving on to our final model, we, as Jimmy mentioned, we added additional convolution layers in original architecture as well. And here we increased our number of parameters to 1.4 million. So also we extracted the part that includes the ventricles from the augmented data. So not just randomly augmented it. So here we doubled the learning rate as well, and trained the model on original first trained the model on original sample size of 87 images, and then performed a lateral flip and again trained the model on 174, basically just double the sample size what we had before. And like we used this is so there's something called as fine tuning. So basically we trained whatever we had over here and then double the sample size and trained the model again. And surprisingly, we got overall accuracy of 99.01%, which was basically good than all of the trials we did before. So we tested this model on completely new samples. So Jimmy will explain further our accuracy tests.
So yeah, so using our final model to test on the completely new samples that we created, we, as we can see from here, we from the left side, sample 98, we were able to have predictably correctly predicted about 84%, which is the sensitivity of our models is 84%. And as you can see visually on the slide, you can see that it correctly segmented out the ventricles. But however, when you go to the right side with sample 99, provided that this MRI scan has a smaller ventricle, it has a lower sensitivity of 47%. I do believe that it is our model was able to segment it out like relatively larger ventricles. I do think that if we have more samples and we have more training time, we will be able to accommodate the smaller ventricles and have a higher sensitivity for that. And now Sarah will talk about the weights within our model.
So hello everybody. So we visualize the first convolution layer weights. Why? Because once we have a model, the emergence of patterns inside the weights can give us insight about what the network learned to recognize, and also it can intuitively show that actually the network learned something. In order to do so, we compared the weights of a trained network with the weights of an identical but untrained model that thus has random weights. The 3D nature of the filters posed a challenge. And in order to solve this, what we did is that we visualized the weights in two ways. First of all, we sliced the matrix of the filter in one of its 3 dimensions. And also we visualized the matrix as a 3-dimensional plot. The weights were first normalized for a range of values between 0 and 1, and then they were plotted with a diverging color map. Can you show the next slide, please? So as we can see, this is the final model, the one that had the best results. And we can see the difference between the untrained model and the trained model. As we can see, the weights are not random anymore. However, the size of a kernel is just 3 by 3 by 3. And for this reason, it's too small to actually be able to clearly recognize pattern. For this reason, we analyze also the weights of a model that had a first layer of size 7 by 7 by 7 that is shown in this next slide. So as we can see here, the visualization actually shows that the trained model so the trained model shows that the weights are not random. As we can see from the comparison with the untrained model. However, we still don't recognize clear patterns. Why? As we can see in our next slide, so here we can see that, yes, the model, actually the network learned to recognize, to do the segmentation somehow, but the results are not yet as much good as the other model. And we can see even if it learned something, the training wasn't long enough for enough epochs, or it has to be done in a different way in order to get as much prediction as the other model. However, the network learned something, and for this reason, the weights are not anymore random. Next slide, please.
Thanks, Sarah. So we believe that these are the improvements and future development our project could have. So basically, the improvement we needed the most was to increase the number of data samples by basically just manually segmenting out the ventricles so as to we would had more samples. So also more samples means more utilization of computational power. So we could then further we can set up Google Cloud Platform to do our computational task. Also, we wanted to try a loss function which is a weighted binary cross entropy. So which will basically penalize for correctly penalize the for predicting. We can add heavy penalty for predicting zeros. And so the future work of this project will be to segment out multiple features from the brain's MRI scan. For this project, we just did the ventricles, but future work will include more number of samples and multiple features segmenting out. So yeah, these are the references. And thank you so much. Please feel free to ask your questions. Thank you.
All right, thank you guys so much. And again, sorry that you had to redo that. All right. Well, thank you guys, and this is a good project, and I will get a meeting with Z Imaging set up for next week. Please tell me if you have any constraints on when you can meet, and I'll try to work around things.
Okay.
Thank you.
Thank you very much.
Thank you so much, Professor.
Absolutely.
Thank you. Also, thank you for moving the presentation a bit earlier. Thank you so much.
Yeah, no worries. All right, take care.
Thank you. Take care. Bye-bye.
Thanks.
Bye.